The universe is filled with countless stars and planets, yet even within this vast abundance, there exists a class of worlds so rare that their very presence feels like a cosmic accident. Astronomers have discovered thousands of exoplanets, and it is believed billions more are waiting in the dark, unseen. But among them lies a category so extraordinary that scientists can count them not in hundreds, nor even in dozens, but on their very fingers, just around 13. Around 13 worlds scattered across the galaxy like hidden diamonds in an endless desert of stars. They are rarer than gold, rarer than diamonds, and rarer than almost anything else we have uncovered in the universe. These are the circumbinary planets, celestial survivors orbiting not one star, but two, defying the violent gravitational chaos of dual suns to carve out their place in the cosmos. Having uncovered just how rare these celestial diamonds are, it becomes essential to understand what truly sets them apart from the thousands of other worlds we've cataloged. If Earth is ordinary because it orbits a single star, then circumbinary planets exist in a realm that feels almost unreal. These are planets that orbit two stars at once, bound to the gravitational pull of a binary system. Unlike our home world, which peacefully circles one steady source of light and heat, circumbinary planets must survive the gravitational push and pull of two stellar bodies locked in their own intricate orbital dance. This means their reality is far more complicated than ours. Every sunrise, every orbit, every change in climate is shaped by the unpredictable interaction of two suns sharing dominance over one world. To grasp how unusual this is, imagine the stars themselves. In a binary system, two stars orbit a common center of mass. Sometimes they are close enough to one another that they whirl tightly like dancers holding hands, and other times they are separated by a vast gulf, moving in an elongated path that takes hundreds or even thousands of years to complete. Now, add a planet into this equation. For it to orbit both stars, it must stay far enough away that it doesn't get pulled apart by their gravitational tug-of-war, but close enough to remain bound to the pair. This delicate balance is not something nature produces often. In fact, for many decades, astronomers believed circumbinary planets might be impossible to exist at all. The chaotic dynamics of two stars suggested that any planet trying to orbit them would either be ejected into deep space or pulled into one of the stars, destroying it before it had a chance to settle. And yet, against all odds, we now know that they do exist. Their orbits are typically wider, encompassing both stars together, as if wrapping them inside a single gravitational bubble. This makes their year a measurement of the time it takes to circle both stars, not just one. From a distance, they might look deceptively stable, but their stability is earned through an invisible battle between competing gravitational forces. Each moment, the planet is being pulled by two stars of differing masses, brightness, and activity levels. Some of these stars are calm and steady, while others flare violently with bursts of radiation that would scorch any nearby world. A circumbinary planet has no choice but to endure both masters, surviving in the middle of what seems like chaos designed to destroy it. The uniqueness of these planets doesn't end with gravity. Their skies are unlike anything humans could ever experience on Earth. On some of these worlds, there would be two suns blazing during the day, sometimes close together in the sky, sometimes drifting apart, even creating the illusion of double shadows stretching across the landscape. Depending on the alignment, one star might rise before the other, giving a planet two sunrises in succession, followed by two sunsets. The very rhythm of time itself, as measured by day and night, would be different, shaped not by one steady sun, but by the intricate dance of two. If one star is larger and brighter, its dominance might drown out the second star during much of the day, yet the second would still rise and set, painting the horizon with colors and angles of light that no single sun planet could replicate. For life, if it could exist there, the experience of time, heat, and light would be unlike anything our species has ever known. This dual star environment also challenges the very concept of habitability. On Earth, the conditions that allowed life to emerge depend on the relatively stable energy output of a single sun. A planet with two stars, however, must contend with fluctuating levels of light and heat, complex shadowing, and unpredictable radiation patterns. While these worlds are fascinating to imagine, the idea of them supporting life as we know it seems far less likely. Yet, at the same time, their existence expands our understanding of what's possible. If planets can survive here, thriving in the gravitational chaos of two suns, then perhaps life itself is far more adaptable and widespread than we currently believe. What makes circumbinary planets even more captivating is that they force scientists to rethink planetary formation itself. Conventional wisdom suggests planets form from the leftover material of a star's creation: dust, gas, and ice coalescing into rocky or gaseous bodies in orbit around a single stellar mass. But in a binary system, there isn't just one dominant gravitational anchor. There are two. Their combined gravity stirs the protoplanetary disk, creating turbulence, instability, and collisions at rates much higher than in a single star system. For a planet to successfully emerge from this chaos, the material must somehow coalesce and stabilize without being shredded apart. That this process has occurred at least around 13 times, enough to create the confirmed circumbinary planets we know, reveals that nature is even more resourceful than our models suggest. It is also worth noting that circumbinary planets are not the same as planets orbiting one star of a binary system, which is actually more common. Many planets orbit a single star, while its companion star lingers at a greater distance. But a true circumbinary planet doesn't belong to just one. It orbits both simultaneously, wrapping around their shared gravitational center. This distinction is what makes them so unique. They are not just rare, they are almost paradoxical, defying expectations by existing in a place where survival should be nearly impossible. Having understood what circumbinary planets are, the next question almost asks itself: if binary stars are so common across the galaxy, why are there so few planets orbiting them? The answer lies in the fundamental instability of two-star systems. Unlike our Sun, which exerts a steady, centralized gravitational pull, binary stars are constantly tugging at one another, their gravity weaving an intricate web of chaos. For any planet to survive in such an environment is nothing short of miraculous. The laws of physics conspire against their formation, against their stability, and even against their long-term survival. It is this perpetual chaos that explains why astronomers have confirmed only around 13 of these planets out of the thousands of exoplanets we know about. The very birth of a circumbinary planet is fraught with challenges. In a single-star system, a protoplanetary disk of dust and gas can gradually coalesce into planets over millions of years, with relative calm guiding the process. But in a binary system, this disk is anything but calm. The two stars orbiting one another stir the surrounding matter violently, scattering dust, destabilizing regions, and triggering collisions at destructive speeds. It is as if the womb from which planets are meant to be born is constantly being shaken. This turbulence makes the odds of material clumping together into a stable planet staggeringly low. Even if matter does begin to gather, the irregular gravitational forces can easily tear it apart before it has a chance to grow into anything significant. For those rare cases where a planet does form, the challenge of survival is only beginning. The constant dance of two stars creates regions of gravitational instability where orbital paths become dangerous zones. A planet straying too close to either star risks being ripped away or hurled into interstellar space, banished from its system entirely. This is why most planets in binary systems are not circumbinary at all. They orbit just one of the two stars while keeping the other at a safe distance. To orbit both stars together, a planet must settle into a very precise range of stability, a narrow band where the combined gravitational pull of both stars balances out just enough to allow a stable orbit. Step outside this range and the planet's fate is sealed. It either collides with one of its suns or is ejected into the darkness between stars. This fragile balance is the cosmic equivalent of walking a tightrope in a storm. A slight shift in the binary star's orbit, a flare of stellar activity, or the presence of another celestial body could throw everything off. It takes extraordinary precision for a circumbinary planet to remain intact, and yet the universe has managed to craft at least around 13 of these delicate survivors. Each one is not just a planet, it is a triumph over the very chaos that seeks to destroy it. What adds another layer of rarity is the issue of time. Binary stars themselves evolve, sometimes swelling, shrinking, or shifting as they age. A planet orbiting them must adapt to these changes without losing its balance. The instability isn't just at the moment of formation, but continues across billions of years. Many planets that may have once orbited two stars could have been lost to time, scattered into space as their parent stars grew restless and changed their gravitational relationship. What we see today, around 13 known circumbinary planets, may be just the survivors of an untold number of failed attempts by the universe to sustain such worlds. It's this combination of factors, turbulent birth, fragile survival, and the relentless instability of time, that makes circumbinary planets so rare. Their scarcity is not due to a lack of binary stars, but because nature itself stacks the odds against them. The few that exist are cosmic outliers, exceptions to the rule, reminders that even in the most hostile conditions, improbable wonders can emerge. In a galaxy where nearly half of all stars are part of multi-star systems, the fact that only around 13 circumbinary planets have been confirmed underscores just how extraordinary they are. The story of circumbinary planets would have remained nothing more than an intriguing theory, if not for one of humanity's most ambitious space observatories, the Kepler Space Telescope. Before Kepler, astronomers speculated about the possibility of planets orbiting two stars, but the instability of such systems made many skeptical. Could nature truly allow such delicate orbits to exist? The idea lingered at the edges of imagination, more the stuff of science fiction than astrophysics. That changed dramatically in 2011, when Kepler delivered a revelation that would permanently alter our understanding of the universe: the confirmed detection of the very first circumbinary planet. This groundbreaking discovery was named Kepler 16b, and it immediately captured the world's imagination. For the first time, we had undeniable proof that a planet could orbit two stars at once. The system lies roughly 200 light-years away in the constellation Cygnus, and at its heart are two stars, one slightly smaller and cooler than our Sun, the other a faint red dwarf. Together they orbit one another in a cosmic dance that repeats every 41 days. Circling both of them, like a silent witness to their endless motion, is Kepler 16b. The planet itself is a gas giant, similar in size to Saturn, meaning it is not a rocky, Earth-like world, but its existence was monumental. It proved beyond doubt that the chaotic gravitational forces of binary stars could indeed cradle a planet in a stable orbit. What had once been dismissed as improbable suddenly became real. Kepler 16b's discovery was not just a triumph of science, it was also a cultural milestone. Almost instantly, it drew comparisons to the desert planet Tatooine from the Star Wars universe, famous for its double sunsets. For decades, twin-sun worlds had been relegated to the realm of fiction, but here was a genuine celestial body that mirrored the imagination of storytellers. The breathtaking thought of standing on a planet's surface and watching two stars rise and fall across the horizon was no longer fantasy, it was confirmed science. Though Kepler 16b is far too hostile for life as we know it, its very existence suggested that the universe might hold other circumbinary planets where conditions could one day be suitable for biology. The method of discovery itself was as extraordinary as the planet it revealed. Kepler's mission was designed around the transit method, a technique that detects planets by observing the tiny dips in a star's brightness when a planet passes in front of it, blocking a fraction of its light. But in the case of Kepler 16b, this was far more complex. With two stars, the patterns of brightness fluctuations were far more tangled than in a single star system. Kepler had to detect not only the stars eclipsing one another as they orbited, but also the planet as it crossed in front of both stars at different times. This triple interplay of transits created a signature so unusual that it could only be explained by the presence of a planet orbiting the entire binary pair. It was a breathtaking confirmation of both human ingenuity and the universe's ability to surprise us. Kepler 16b's orbit is another marvel of cosmic precision. The planet circles its twin suns at a distance of about 65 million miles, slightly closer than Venus is to the Sun. Yet unlike Earth or Venus, which orbit a single gravitational anchor, Kepler 16b must contend with two. The stars themselves are locked in a tight orbit with each other, and the planet orbits around both of them, as if they were a single body. What makes this so extraordinary is its stability. For years, computer models had predicted that such orbits might be possible, but Kepler provided real, observed evidence. The planet's orbit is nearly circular and remarkably steady, despite the gravitational complexity of its system. Against all odds, Kepler 16b has found a way to thrive in one of the harshest gravitational environments imaginable. The discovery did more than confirm the existence of circumbinary planets. It also unlocked a floodgate of new possibilities. If one planet could be found, surely there were others waiting to be discovered. Kepler's unprecedented ability to monitor more than 150,000 stars at once gave astronomers the perfect tool to continue searching. And indeed, in the years following Kepler 16b, additional circumbinary planets were confirmed, each adding a new piece to the cosmic puzzle. But it was that first detection that shattered centuries of doubt, proving that the universe is far stranger and more creative than we often allow ourselves to imagine. The significance of Kepler 16b extends beyond scientific novelty. It forced astronomers to rethink long-standing theories about planetary formation. Before this, most models suggested that the chaotic conditions of binary systems would shred protoplanetary disks, preventing planets from forming at all. Yet Kepler 16b exists, showing that even in turbulence, stability is possible. Its presence hints that circumbinary planets may be more common than we realize. They're simply harder to detect. For every confirmed discovery, there could be dozens more hidden from our view, their unusual orbits preventing us from catching them in transit. The first discovery didn't just prove existence, it suggested a hidden abundance waiting to be uncovered. The sheer improbability of finding such a planet also underscores the power of persistence. Kepler's telescope was not designed specifically to hunt for circumbinary planets. Its mission was to find Earth-sized planets in habitable zones. And yet, by patiently staring at stars for years, it uncovered something no one had ever seen. The lesson here is profound. Sometimes the most extraordinary discoveries emerge not from searching for the fantastical, but from watching the ordinary long enough for the extraordinary to reveal itself. The discovery of the first circumbinary planet was a scientific triumph, but what truly captivated the imagination of both scientists and the public was not the math, not the orbital diagrams, and not the detection graphs. It was the vision of what such a world might look like. If standing on Earth gives us the familiar rhythm of one sunrise and one sunset, then standing on a circumbinary planet would plunge us into a spectacle beyond anything our species has ever witnessed. This is the double sunset effect, a breathtaking celestial performance in which two suns rise and set, painting the skies with layers of light that shift, blend, and dance in ways our single-star world could never produce. On such a planet, daybreak is not simple. Depending on the alignment of its stars, one sun may rise first, cresting the horizon in a blaze of golden light, while its companion follows moments, or even hours, later, spilling an entirely different shade of brilliance into the sky. Imagine dawn beginning with a cool, reddish glow from a small, dim star, only to be overpowered by the fierce blaze of a larger, hotter companion shortly after. Shadows would stretch, shrink, and double themselves in surreal patterns across the ground. The world would awaken not to a single rhythm, but to a layered choreography of light and time. As the day progresses, the spectacle becomes even more remarkable. If the stars are close together, they may climb the sky almost hand in hand, radiating light that overlaps into a brilliance more intense than anything Earth experiences. The sky could take on hues we cannot fully imagine, a fusion of colors where two different stellar energies meet. If the stars are farther apart, however, one might dominate the noon sky while the other lingers lower, creating a constant double source of light. Days would feel strange, alien, neither star providing the steady dominance our sun does, but instead weaving a dynamic interplay of heat, light, and shadow. And then comes evening. On Earth, the sun sets in a slow, graceful fade, drawing shadows long across the landscape until darkness falls. But on a circumbinary planet, sunset can occur twice. One star may dip below the horizon, painting the sky in amber and purple as the light fades. Yet darkness never fully arrives, because the second star still burns brightly above. Minutes, hours, or perhaps even longer later, the second star sets as well, casting an entirely new wave of color across the atmosphere. The world is plunged into true night only after this second curtain falls. The emotional resonance of such a scene is difficult to put into words. It would feel as though the planet itself were receiving two farewells every evening, two reminders of the fragile beauty of light before surrendering to the stars of the galaxy beyond. But sunsets are only one side of the story. Imagine a night under two rising suns. One might appear at the horizon while the other still hangs low in the pre-dawn darkness. The world would shift from cold starlight into a layered glow, one sun tinting the land with pale light while the other spills warmth in a second wave. Depending on the size and color of the stars, these sunrises might feel otherworldly, one star casting orange brilliance while its smaller companion fills the air with soft crimson or even white-blue radiance. To any living being standing on such a surface, dawn would not just mark a beginning of a day, but an unfolding sequence, a celestial duet. This constant interplay of light would also affect the very fabric of existence on these planets. Double shadows would stretch across the ground, sometimes long and sharp when the stars are apart, sometimes overlapping into ghostly blurs when they move closer together. Colors would shift unpredictably throughout the day as the balance of light from each star changed, painting landscapes with hues that would look alien to human eyes. Even the concept of night might be foreign, depending on the orbital dynamics. In some systems, at least one sun might always hover above the horizon, making true darkness nearly impossible except in rare alignments. The circadian rhythms of life, if life could exist, would be shaped not by a steady cycle of light and dark, but by a shifting, overlapping sequence of multiple day-night transitions. From the perspective of physics, these double sunsets are more than aesthetic. They demonstrate the delicate orbits that allow circumbinary planets to exist. The timing of the rises and sets reflects the relative positions of the stars and the planet's orbit around them. Sometimes the stars align closely, making their rises and sets nearly simultaneous. Other times, they separate widely, creating staggered moments of brilliance. This variation is yet another reminder of how fragile these systems are. Each shift in orbit, each gravitational tug, changes the choreography of the skies. What seems like beauty is also survival, a visual reminder of the balance these planets must maintain in order to endure. The awe-inspiring double sunsets of circumbinary planets make them sound like something out of a dream. But before we could ever picture their surreal skies, astronomers first had to prove they were real. This proof did not come from simply looking up into the night with powerful telescopes, but from a painstaking and ingenious method of detection that has revolutionized the way we discover exoplanets. This is known as the transit method, and it is the very technique that allowed us to find the first circumbinary planets hiding among the stars. At its core, the transit method is beautifully simple, though executing it requires extraordinary precision. Stars emit steady light across vast distances, and to us, that light appears consistent. But if a planet happens to pass, or transit, in front of its parent star from our vantage point, it blocks a tiny fraction of that light. The result is a subtle dip in brightness, almost like a star blinking ever so slightly. These dips can be measured, and when they occur at regular intervals, astronomers can deduce that a planet must be orbiting the star. For single-star systems, this technique has been wildly successful, leading to the discovery of thousands of exoplanets. However, detecting a planet in a binary system is far more complex. Instead of a single, steady source of light, circumbinary systems involve two stars orbiting one another, and their light already fluctuates as they eclipse each other. From Earth, we might see one star pass in front of the other, producing natural dimming events that repeat regularly. These variations are challenging enough to untangle, but when a planet joins the system, it adds another layer of complexity. The planet can transit in front of one star, then the other, or even both in sequence. Each event produces a unique signature in the brightness of the system. What results is not a neat, predictable pattern, but a chaotic tapestry of light fluctuations that require careful analysis to decipher. The brilliance of the Kepler Space Telescope lay in its ability to sit and watch with unwavering patience. Instead of snapping images, Kepler continuously measured the brightness of over 150,000 stars, capturing every tiny variation with precision, down to fractions of a percent. For circumbinary planets, this vigilance was crucial. A planet crossing in front of one star might only dim the system's brightness by less than 1/100th of a percent, and because both stars are moving in their own orbit, no two transits are exactly alike. The dips in light occur at irregular intervals, sometimes shorter, sometimes longer, depending on the relative positions of the planet and its twin suns. Only by gathering thousands of hours of continuous data could Kepler untangle these signals and confirm that the dimming wasn't just the stars themselves, but the shadow of a planet orbiting both. One of the most striking features of using the transit method for circumbinary planets is the way it produces multiple signals for a single world. On Earth, If we were to observe a planet transiting one star, we'd expect a consistent dip every orbital period. But for circumbinary planets, the planet can pass in front of star A, then later in front of star B, each creating different depths and durations of dimming. Sometimes, it even transits while the stars are eclipsing each other, producing especially unusual patterns. These overlapping signals are what makes circumbinary planets so difficult to detect, but also so unmistakable once identified. No other phenomenon can replicate such intricate light curves. It is the cosmic fingerprint of a planet orbiting two stars. Beyond confirming their existence, the transit method also allows astronomers to measure key properties of circumbinary planets. The size of the dip reveals the planet's size relative to its stars. The timing of the transits provides clues about its orbital period and distance. Even the irregularities in those timings can tell us how the gravitational tug-of-war between the two stars influences the planet's path. In effect, by carefully analyzing faint flickers of light across time, scientists can reconstruct the architecture of entire star systems light years away. It's worth noting that while the transit method is powerful, it is also inherently limited by geometry. To detect a planet, its orbit must align just right with our line of sight, so that it crosses in front of its stars from Earth's perspective. For single-star systems, this already means we miss the vast majority of planets whose orbits don't align perfectly. For circumbinary systems, the odds shrink even further because the stars themselves are moving and shifting in their orbit. This is one of the main reasons circumbinary planets are so rare in our observations, not necessarily because they don't exist, but because catching them in the act of transit is incredibly unlikely. Each confirmed detection represents not just a planet, but a stroke of extraordinary observational fortune. The ingenuity of the transit method, however, is that it doesn't just spot the obvious. With enough data, astronomers can confirm planets that transit irregularly, or even only a handful of times, by combining transit observations with models of binary star motion. Kepler's long-term monitoring gave scientists the tools to distinguish between eclipsing binaries alone and binaries orbited by planets. The discovery of Kepler 16b, for example, came directly from recognizing this unique fingerprint, dips in brightness that could only be explained by a planet orbiting two suns. The transit method gave us the breakthrough we needed to prove circumbinary planets exist, but it also exposed just how incredibly difficult these worlds are to detect. With ordinary exoplanets orbiting a single star, astronomers already face the enormous challenge of alignment. Only a small fraction of planets in the galaxy happen to pass directly between their star and Earth in such a way that we can observe their transits. For circumbinary planets, this difficulty grows exponentially, because their orbital paths are not simple circles around one gravitational anchor. Instead, they are tangled within the complex, shifting geometry of two stars orbiting each other, making their alignment with our telescopes a fleeting and rare occurrence. The key problem lies in the messiness of their orbits. In a binary system, the two stars orbit a shared center of mass, and that center itself is in motion. A circumbinary planet must orbit this moving gravitational focal point, which means its trajectory is not fixed in a perfect, predictable ellipse the way Earth's orbit is around the Sun. Instead, the orbit constantly shifts, tilts, and precesses over time. For astronomers, this means that even if a circumbinary planet happens to transit its stars from Earth's perspective, it may not do so consistently. A planet might transit during one part of its orbital cycle, only to completely miss the stars in subsequent cycles as its orbital plane drifts out of alignment. This irregularity makes catching a transit far more dependent on both timing and luck. Imagine trying to watch a distant clock pendulum through a narrow slit. If the pendulum swings in the same plane each time, you'll always see it pass through the slit regularly. But if the pendulum shifts angles with every swing, sometimes you'll catch it, and sometimes you won't. That is essentially the problem astronomers face with circumbinary planets. The star's orbital motion causes the apparent angle of the planet's path to wobble, making transits appear irregular or vanish for years at a time. This effect, known as orbital precession, can cause a planet to hide from detection even though it is still orbiting normally. Kepler's mission was uniquely suited to overcome some of these challenges because it stared at the same patch of sky continuously for years. This long-term vigilance meant that astronomers could observe rare and irregular transits that would have been missed in shorter surveys. But even Kepler had limitations. For some circumbinary planets, the transits were so rare and uneven that only a handful could be recorded during the telescope's operational lifetime. In other cases, astronomers detected strange light fluctuations but couldn't gather enough data to confirm the presence of a planet with certainty. This is why, despite knowing of thousands of exoplanets, only around 13 circumbinary planets have been officially confirmed. Many more candidates may exist, but the irregularity of their signals keeps them in the category of suspected rather than proven. Another complication is that binary stars themselves are noisy systems. They often eclipse each other, producing dramatic dips in brightness that can dwarf the subtle signal of a transiting planet. Stellar activity, such as flares, spots, and pulsations, adds further noise to the light curve, making it even harder to tease out the delicate fingerprint of a circumbinary planet. The transit method relies on distinguishing these tiny dips from the background fluctuations. And when the background is chaotic, the task becomes like finding the faint outline of a shadow in the middle of a storm. Because of these difficulties, astronomers have turned to additional techniques to complement the transit method. One of these is eclipse timing variations, ETVS. In binary systems, the two stars regularly eclipse each other, and the timing of these eclipses should be consistent. But if a planet is orbiting them, its gravitational pull can cause slight variations in when the eclipses occur, sometimes earlier, sometimes later. By measuring these tiny shifts, astronomers can infer the presence of a circumbinary planet even when transits are not visible. Still, this method is delicate, requiring years of careful observation to build confidence. These challenges highlight why circumbinary planets are so elusive. It's not necessarily that they are extremely rare in existence, but that they are exceptionally rare in detectability. The universe may contain far more than around 13 of these worlds, perhaps dozens or even hundreds hidden across the galaxy, but our current methods can only catch them in very specific circumstances. A circumbinary planet must not only exist and survive the chaos of two suns, but also align with Earth in precisely the right way at the right time for us to catch its fleeting shadow. The odds are stacked overwhelmingly against detection, which is why every confirmed discovery feels like a cosmic stroke of fortune. In many ways, this difficulty adds to their mystique. They are not just planets. They are planets that hide, planets that evade detection by slipping between the blind spots of our instruments. Each one we confirm feels like a secret pulled from the universe, a whisper of worlds that are mostly invisible to us. The struggle to find them is part of what makes them so rare and precious in our catalog of cosmic discoveries. The difficulty of detecting circumbinary planets cannot be overstated. Their messy, shifting orbits, irregular transits, and chaotic star systems make them some of the most elusive objects in the cosmos. If astronomers had relied only on traditional ground-based telescopes or shorter observational surveys, these planets might still exist only as speculative theory. But fate and human ingenuity aligned in the form of one extraordinary mission, the Kepler Space Telescope. Kepler was not just another observatory. It was uniquely positioned, designed, and operated in a way that gave it an unparalleled advantage in uncovering the hidden worlds orbiting twin suns. Without Kepler, the rare beauty of circumbinary planets might still be lost to us, concealed behind the noise of stars and the sheer improbability of alignment. At the heart of Kepler's advantage was its singular focus. Unlike most telescopes that scan across wide regions of the sky, shifting between targets, Kepler was built to stare at a single patch of the heavens continuously and without interruption. For nearly a decade, it monitored over 150,000 stars in a region of the Milky Way near the constellations Cygnus and Lyra. This tireless vigilance was crucial. Circumbinary planets, as we've seen, don't transit in neat, predictable intervals. Their dips in starlight are irregular, sometimes occurring with gaps of months or years, depending on the complex interplay of their orbits. Only by watching stars relentlessly for thousands upon thousands of hours could Kepler hope to catch these fleeting and irregular events. It was not just a telescope, it was a cosmic detective with infinite patience. Another key to Kepler's success was its extraordinary sensitivity. The transit method relies on detecting dips in starlight as small as a fraction of a percent. For Earth-sized planets transiting Sun-like stars, the dimming can be less than 0.01%. Such subtle changes are impossible to track from Earth's surface, where the atmosphere constantly distorts starlight. Kepler, floating far above the blurring effects of our air, could measure brightness with unmatched precision. This precision meant that even in the noisy light curves of binary stars, where stellar eclipses and fluctuations created confusion, Kepler could detect the faint secondary signals of a planet slipping across the face of its suns. It was the difference between trying to hear a whisper in a crowded room and having a microphone tuned to amplify only the faintest voices. But perhaps the most remarkable advantage of Kepler was its ability to capture complex, multi-layered light curves and interpret them as planetary signatures. In binary star systems, the light dips are anything but straightforward. The stars eclipse each other, creating deep, predictable dimmings. Add a planet to the mix, and the light curve becomes a tapestry of overlapping events, shallow dips from planetary transits, deep dips from stellar eclipses, and irregular timings due to orbital precession. For most instruments, this would look like noise. But Kepler's long-term dataset allowed astronomers to disentangle the signals, recognizing the unique fingerprints of circumbinary planets. When Kepler observed Kepler 16b, the first confirmed circumbinary planet, it was able to separate the overlapping transits and prove conclusively that the dips in brightness came not just from the stars, but from a planet orbiting both. Another element that gave Kepler an edge was its ability to track timing variations. Circumbinary planets often reveal themselves indirectly through the gravitational tug they exert on their host stars. When two stars eclipse each other, the timing of these eclipses is normally consistent. But if a planet orbits them, its gravitational influence can cause the eclipses to occur slightly earlier or later than expected. These variations are minute, often measured in seconds, but Kepler's precision was sharp enough to detect them. This allowed astronomers to confirm circumbinary planets even when their transits were sparse or inconsistent. Without this level of accuracy, many of these worlds would have remained hidden, their shadows lost in the chaos of binary starlight. The mission's sheer duration was another critical factor. Kepler launched in 2009 and, until its retirement in 2018, gathered nearly a decade of continuous data. For circumbinary planets with longer orbits, some taking years to complete a single revolution, this was the only way to catch enough transits to confirm their existence. A planet might transit once early in the mission, then not again until several years later. Shorter surveys would have written off such signals as anomalies. Kepler's endurance gave astronomers the long view necessary to piece together the puzzle. And yet, Kepler's advantage was not just technical, it was philosophical. The mission represented a shift in how humanity approached the search for other worlds. Before Kepler, the discovery of exoplanets was sporadic, often relying on indirect techniques like measuring stellar wobbles or gravitational microlensing. Kepler was the first mission dedicated to hunting planets systematically, with the explicit goal of determining how common planets are in our galaxy. This dedication is what allowed circumbinary planets to emerge from theory into reality. Kepler was not designed specifically to find them, but its relentless data collection made their discovery inevitable. The telescope's success was a triumph of patience, perseverance, and the willingness to let the universe surprise us. Kepler's legacy in circumbinary planet research is monumental. Without it, we might still think such worlds were only possible in science fiction. Instead, Kepler gave us around 13 confirmed examples, each one a cosmic jewel orbiting in defiance of chaos. It showed us that planets could form and survive in places where models once predicted destruction. It proved that the universe is not just stranger than we imagine, it is stranger than we can imagine. And it left behind a treasure trove of data that astronomers continue to mine, even years after the telescope's retirement. Hidden in that data may still be undiscovered circumbinary planets, waiting for the right analysis to reveal their presence. The Kepler mission gave us our first confirmed glimpses of circumbinary planets, lifting them from the realm of speculation into the solid ground of discovery. But as soon as astronomers realized these worlds were real, an even bigger question emerged. Just how many of them might exist beyond the handful we've already found? The official count today stands at around 13 confirmed circumbinary planets. Yet scientists strongly suspect this is only the tip of the iceberg. Based on Kepler's data and models of binary systems, Researchers estimate there may be 17 or more circumbinary planets already lurking in the data, waiting for confirmation, or possibly hiding beyond our current ability to detect them. The rarity, then, is not necessarily in their existence, but in our capacity to catch them in the act. One of the main reasons for this suspicion lies in the sheer abundance of binary stars. Nearly half of all stars in our galaxy are part of multi-star systems, with binaries making up a significant portion of them. If planets can form in such chaotic environments at all, and Kepler proved they can, then statistically there should be far more than a dozen scattered across the Milky Way. The discrepancy comes from the extreme difficulty in detection. As we've seen, the transit method requires precise alignment. For every circumbinary planet we've caught, countless others are likely orbiting at angles that never line up for us to observe their silhouettes against their suns. This cosmic geometry problem means our current discoveries are probably a small fraction of the true population. The number 17 comes from candidates Kepler flagged, but that haven't yet passed the rigorous tests needed to confirm them. In the language of astronomy, a candidate is a planet-like signal that could be the real thing, but still carries the risk of being explained away by other factors: stellar activity, data noise, or misinterpretations of binary star dynamics. These candidates often look promising, but confirming them requires either repeated transits or complementary observations that aren't always possible. Some of the suspected circumbinary planets have transit intervals so long and irregular that Kepler simply didn't last long enough to observe multiple passes. Without a repeat, their status remains in limbo, tantalizingly close to certainty, but not quite there. Another reason scientists believe in a hidden population of circumbinary worlds is the remarkable consistency of patterns in the confirmed planets. For example, many of them orbit at just the right distance to maintain long-term stability, close enough to remain bound to their stars, but far enough to avoid being ripped apart by gravitational chaos. This suggests that planet formation in binary systems, while rare, follows predictable pathways. If nature found these stable niches in around 13 systems, it likely found them in many more. The challenge is simply proving it with data. In addition, computer simulations of protoplanetary disks around binary stars show that circumbinary planets should be able to form more often than our observations suggest. These models demonstrate that, while turbulence and instability do make planet formation harder, certain regions around binary stars remain relatively calm. These islands of stability are exactly where the confirmed circumbinary planets have been found. If simulations are correct, then planets should occupy these zones in far more systems than we've currently detected. The fact that we've already stumbled upon around 13, despite the enormous odds against alignment, hints strongly that there are many others hidden from our line of sight. Beyond Kepler, astronomers are turning to new missions and telescopes to continue the search. The Transiting Exoplanet Survey Satellite, TESS, has already added to the pool of exoplanet discoveries, though its shorter observation windows make finding circumbinary planets more difficult. The upcoming Plato mission from the European Space Agency, along with the powerful instruments of the James Webb Space Telescope, hold promise for detecting and studying these elusive worlds in greater detail. These new tools could finally confirm the suspected candidates and potentially uncover entirely new populations of circumbinary planets that Kepler couldn't see. The possibility of hidden worlds raises a fascinating philosophical point. For every circumbinary planet we know, there may be dozens more that we will never detect simply because of orientation. The galaxy could be teeming with these rare survivors, but to us, they remain invisible. Worlds that exist but might forever elude human confirmation. It is a humbling reminder of the limits of our perspective. We are like explorers, peering through a narrow keyhole at a vast landscape, able to glimpse only what chance alignment places in our field of view. Still, even the suspicion of more circumbinary planets expands our understanding of the universe. The confirmed around 13 are enough to prove their existence, but the hidden candidates remind us that discovery is an ongoing process. The universe rarely reveals its secrets all at once. Instead, it whispers them, one faint light dip at a time, daring us to keep watching, keep questioning, and keep building the tools to see more clearly. For circumbinary planets, the story is far from over. What we've seen may only be the beginning, a handful of jewels pulled from the dark, hinting at a treasure trove still buried among the stars. If the suspected 17 eventually grow into confirmed numbers, or if future missions uncover dozens more, Circumbinary planets may shift from being the rarest of the rare to a small but significant category of worlds. Until then, they remain cosmic enigmas, half known, half hidden, straddling the line between theory and proof. And perhaps that mystery is part of their allure. They are not just rare because they are few, but because they remind us how much of the universe is still waiting to be uncovered. Circumbinary planets are already extraordinary for the mere fact of their survival, but their environments take their strangeness to another level. When a planet orbits two suns instead of one, the conditions on its surface, or within its atmosphere, become wildly more complex than anything we know on Earth. Our planet enjoys the relative stability of a single star, the Sun, which provides a consistent rhythm of day and night and a fairly predictable balance of heat and light. But for circumbinary worlds, two suns mean chaos, chaotic heat patterns, shifting light cycles, and climates that can swing from scorching to freezing in unpredictable ways. These are not just rare planets. They are extreme environments where the rules of habitability are rewritten entirely. At the most basic level, two stars mean two competing sources of heat and light. If the stars are similar in size and brightness, the planet may experience overlapping days where both suns dominate the sky at once, flooding the surface with intense radiation. Temperatures could spike far higher than on Earth, even if the planet orbits at a distance similar to ours. Conversely, when both stars happen to set at nearly the same time, the world could be plunged into sudden and total darkness, causing equally sharp drops in temperature. These rapid fluctuations between extremes would make the planet's surface highly unstable, challenging the very idea of a consistent climate. Now imagine if the stars are very different. Many binary systems pair a bright, sun-like star with a much smaller, cooler red dwarf. In this case, the heat patterns would be asymmetrical. The larger star would dominate during most of the planet's orbit, creating conditions similar to, but harsher than, a single-star system. The smaller star, however, would still contribute heat and light, producing a strange secondary cycle that overlays itself onto the larger star's rhythm. The result is a climate with multiple layers of complexity. Hot peaks when both stars shine together, cooler intervals when only one star is visible, and occasional plunges into cold if the stars eclipse each other, cutting off much of the light. The orbital motion of the stars themselves further complicates the situation. Since the stars orbit each other, the distance between them from the planet's perspective is constantly changing. Sometimes the stars align close together, concentrating their light in one region of the sky. At other times, they drift apart, effectively creating two different suns rising and setting at different times. This dynamic relationship means that the planet's heat distribution is never uniform. One hemisphere might bake under the dual glare of two suns, while another cools in partial shadow. Over time, these variations could create a patchwork of climates across the planet. Deserts scorched under double noons, icy regions where the geometry of the orbits leaves long stretches of cold twilight, and transitional zones caught in between. These conditions would have profound consequences for any atmosphere the planet might possess. On Earth, our atmosphere redistributes heat relatively evenly, smoothing out temperature differences between day and night, equator and poles. But on a circumbinary planet, the atmosphere would be forced to cope with radically shifting inputs of energy. Winds could surge with violent intensity as air masses respond to sudden heating or cooling, producing storms on a scale Earth has never seen. Clouds might form and dissipate in unusual patterns, driven by two overlapping cycles of solar heating. Rainfall, if it exists at all, would likely be erratic, localized, and tied to the unpredictable rhythms of the stars. Life under such conditions, if possible, would need to evolve remarkable resilience, capable of withstanding a world where the very definition of climate is unstable. And yet, it's not only the atmosphere that would face extremes, the planet's surface conditions would also be extraordinary. If the world is rocky, like Earth, vast temperature swings could crack and reshape landscapes over time, splitting rocks and sculpting surfaces through cycles of rapid heating and cooling. If the world is an ice planet, double suns might melt large regions during periods of combined brightness, only for them to refreeze when one or both stars set. For gas giants, the complexity would manifest in atmospheric bands, jet streams, and storms unlike any seen in our solar system, driven by layers of radiation that wax and wane unpredictably. Imagine a version of Jupiter's Great Red Spot, but fluctuating in size and intensity as the dual suns alternate in their dominance. One of the most fascinating aspects of these extreme environments is the potential for seasons unlike anything on Earth. Our seasons come from the tilt of our planet's axis and its orbit around a single sun. On circumbinary planets, however, seasons would be shaped not just by axial tilt, but by the motion of two stars. The length and intensity of summers and winters could vary dramatically depending on the positions of the stars in their orbit. Some years might bring unusually hot summers if both stars align to pour maximum radiation onto the planet, while other years might swing toward colder, darker conditions if one star spends more time eclipsed or obscured. These unpredictable multi-star seasons would create an ever-changing climate tapestry, far less predictable than Earth's relatively stable cycle. And yet, amid all this chaos, circumbinary planets still manage to hold on to stability in one sense: their orbits. For all the complexity of light and heat, their paths around two stars remain steady enough for them to survive billions of years. This paradox, stable in orbit, unstable in climate, makes them doubly fascinating. They are planets that endure where they should not, but at the cost of existing under some of the harshest and most alien environmental conditions imaginable. For humans trying to envision what it would be like to stand on such a world, the picture is awe-inspiring but also daunting. You might see two shadows stretching in different directions, one faint and one dark, lengthening and shortening unpredictably as the stars move. The air might feel hot one moment, only to cool rapidly the next, as one sun dips below the horizon. Nights might not even feel like nights at all, illuminated by one lingering star even after the other has set. The ground beneath your feet could swing from burning to freezing within a single rotation, a constant reminder of the volatile heavens above. The extreme environments of circumbinary planets are already enough to make them feel alien beyond comprehension, but when scientists ask the deeper question, the one that drives so much of exoplanet research, things become even trickier. That question is, could these planets support life? To answer it, astronomers turn to the idea of the habitable zone, the orbital region around a star where temperatures might allow liquid water to exist. On Earth, this zone is relatively straightforward to calculate. Our sun provides a steady source of energy, and our planet orbits at just the right distance to keep water from freezing solid or boiling away. But when you add a second sun into the equation, the concept of a habitable zone becomes not only complex, but unstable. On circumbinary planets, the habitable zone itself shifts constantly, making the chances for life far more puzzling than on worlds like our own. The first complication is that two stars provide two sources of energy, and these sources are in constant motion. A planet orbiting them doesn't receive a steady stream of light like Earth does from the sun. Instead, the intensity of radiation rises and falls depending on where the stars are in their orbit. When both stars are aligned on the same side of the planet, their combined brightness can spike temperatures dramatically. When one star passes behind the other, or when they are on opposite sides of the system, the amount of energy drops. The result is a habitable zone that isn't a simple ring around the stars, but a dynamic, shifting region that expands and contracts like a heartbeat. For a planet to remain habitable, it must somehow stay within this moving target, never straying too far toward heat or too far toward cold. To make matters more challenging, the different types of stars in binary systems complicate the picture further. Many circumbinary systems pair stars of unequal size, one bright and hot like our sun, the other smaller and cooler, often a red dwarf. This means the contributions to heating aren't equal. Sometimes the larger star dominates, drowning out the smaller one's effect. Other times, especially when the smaller star aligns just right, its contribution matters more. From the planet's perspective, the total radiation it receives is always fluctuating. For habitability, this means conditions could vary on timescales of days, months, or years, creating an environment where stability is almost impossible. Scientists have tried to model what habitability might look like under such circumstances, and the results are both fascinating and daunting. In some scenarios, a planet orbiting at just the right distance might remain habitable on average, even if the short-term fluctuations are extreme. For example, the average temperature over years or decades might allow liquid water to persist, while the daily or seasonal extremes swing between harsh hot and cold. In other scenarios, however, The fluctuations are so strong that a planet's climate would oscillate beyond survivability. Water boiling away during periods of dual star intensity, then freezing solid when both stars align to minimize heating. The window for stable conditions narrows to a razor's edge. This is one reason why the around 13 circumbinary planets confirmed so far are not considered likely candidates for life. Most of them are gas giants like Saturn or Jupiter, worlds without solid surfaces where biology as we know it cannot take hold. Still, the possibility of habitable moons around such giants remains tantalizing. If a moon orbited within the shifting habitable zone, and if it had a thick atmosphere capable of buffering against extreme fluctuations, life might be able to cling to existence. These moons could, in theory, experience stable enough conditions, especially if their own orbital dynamics provided additional heating through tidal forces. While we haven't yet detected such moons, their potential makes circumbinary systems exciting targets for future research. Another complication is that circumbinary habitable zones don't stay fixed over time. Stars evolve, and as they do, their brightness changes. A binary pair might begin with a habitable zone in one region, only for it to drift outward or inward as the stars age. On Earth, we worry about the sun's slow brightening making our planet uninhabitable in billions of years. On circumbinary planets, that timeline could be much shorter, as the interplay between two evolving stars accelerates the movement of the habitable zone. A planet that was habitable for a few million years might quickly drift into extremes of heat or cold, cutting short the window for life to arise. It's also worth noting that the gravitational forces in binary systems can limit where stable habitable zones exist in the first place. Too close to the stars, and the planet's orbit becomes unstable, pulled apart by their competing gravities. Too far away, and the planet may never receive enough heat to sustain liquid water. The stable habitable zone is often squeezed into a narrow band, and only planets in very specific orbits can survive there. That makes the odds of finding a truly habitable circumbinary planet incredibly slim, especially given how few we've confirmed already. Yet, even with these complications, scientists remain intrigued. Circumbinary planets force us to expand our definition of habitability. On Earth, life thrives in extremes: boiling hot vents on the ocean floor, frozen tundras, acidic lakes. If life can adapt to those extremes here, perhaps it could adapt to the shifting, unstable conditions of a circumbinary world. Instead of a constant climate, life might evolve to survive cycles of plenty and scarcity, heat and cold. On such worlds, survival might not mean comfort but resilience, and the very challenges we see as obstacles could be opportunities for nature's inventiveness. The shifting habitable zones of circumbinary systems already illustrate how precarious life's chances would be on such worlds, but even before scientists could dream of habitability, they first had to ask a more fundamental question: can these planets even survive? For decades, many astronomers believed the answer was no. The violent gravitational tug-of-war between two stars seemed far too chaotic to allow a planet to remain in orbit. Any object caught in that storm, they reasoned, would eventually be pulled apart, flung into interstellar space, or swallowed by one of the stars. Yet, against these expectations, the around 13 circumbinary planets we've discovered prove the opposite. They are not only possible, but remarkably stable, enduring for billions of years in orbits that defy the chaos around them. The skepticism was rooted in the basic laws of celestial mechanics. In a single-star system, orbital stability is straightforward. One dominant gravitational anchor holds the planet in place. But in a binary system, two stars orbit each other around a shared center of mass. Their constant motion means the gravitational field is always shifting, producing regions of intense instability. Early models showed that a planet trying to orbit too close to the stars would be pulled one way, then the other, until its orbit unraveled. The gravitational tides would either hurl it outward into deep space or inward into a fiery collision. For many scientists, this made circumbinary planets seem more like a thought experiment than a reality. The breakthrough came when computer simulations and Kepler's discoveries revealed a crucial truth: stability is possible, but only if the planets orbit at the right distance. This distance is known as the critical radius, a boundary beyond which the combined gravity of the two stars begins to act like a single unified force rather than two competing ones. Inside this radius, chaos reigns. Outside it, planets can find relatively calm paths, orbiting both stars together as if they were one. Every circumbinary planet confirmed so far orbits well beyond this critical zone, where their orbits are stable enough to last billions of years. It is a delicate balance, but once achieved, it becomes surprisingly robust. Kepler 16b, the first confirmed circumbinary planet, is a perfect example. Orbiting at a distance of about 65 million miles, it lies safely beyond its system's critical radius. The result is an orbit so stable that astronomers estimate it could persist for billions of years, surviving as long as the stars themselves. This finding was profound. It showed that while circumbinary planets are rare, those that do exist are not fleeting accidents. They are survivors, locked into stable configurations that allow them to endure the very chaos that once seemed destined to destroy them. What's more, stability in these systems is not just about survival, it's about elegance. The orbits of circumbinary planets are not random or chaotic, but finely tuned, often nearly circular, with only slight eccentricities. This means the planets don't lurch wildly closer and farther from their stars, but instead trace consistent, predictable paths. The very fact that such precision is possible in a double-star system is astonishing. It suggests that nature, through billions of years of trial and error, has found pathways to order even in the most turbulent environments. Stability also matters for another reason. It reshapes our understanding of planet formation. If circumbinary planets had been unstable, we could dismiss them as temporary curiosities, worlds doomed to short lives before being torn apart. But their proven stability means they are integral parts of their star systems, just as Earth is to ours. This forces scientists to rethink how planets form in such environments. Instead of being impossibilities, circumbinary planets must emerge naturally, forming in the outskirts of turbulent protoplanetary disks and migrating inward until they settle into stable zones. Their very existence tells us that planet formation is more adaptable and creative than we once believed. Still, their stability does not mean invulnerability. Circumbinary planets remain at the mercy of long-term stellar evolution. As stars age, they expand, contract, and lose mass, shifting the gravitational dynamics of their systems. A planet stable today might become unstable billions of years from now as its stars evolve. Yet the fact that the around 13 confirmed circumbinary planets are still here means they've already weathered eons of stellar activity. They are not fragile newcomers, but veterans of cosmic survival, each one a living testament to resilience in the face of overwhelming odds. In the broader context of exoplanet discovery, this stability is what elevates circumbinary planets from curiosities to treasures. Each one expands our understanding not only of what kinds of planets exist, but of what kinds of systems can support them. They show that the universe does not conform to simple patterns. Instead, it produces wonders in unlikely places, stable orbits in chaotic skies, and enduring worlds where destruction seemed inevitable. So while many once theorized these planets would be ripped apart by gravity, the reality is far more inspiring. The around 13 circumbinary planets we've confirmed are survivors, not victims. They are cosmic dancers, moving in perfect balance around twin stars, defying the chaos that surrounds them. Their stability is not just a scientific fact. It is a reminder that the universe's creativity often shines brightest in its rarest and most improbable creations. The revelation that circumbinary planets can maintain stable orbits in the midst of gravitational chaos leads us naturally to another staggering truth. Binary stars themselves are not rare at all. In fact, they are astonishingly common. Astronomers estimate that nearly half of all stars in our galaxy belong to multi-star systems, most of them binaries, two stars bound together in a shared orbit around a common center of mass. To put this in perspective, if you were to step outside on a clear night and point randomly at the sky, there is about a 50-50 chance that the star you chose is not alone but is locked in an eternal dance with a companion. The universe, it turns out, is not dominated by solitary stars like our Sun, but by pairs. And yet, amid these countless stellar duos, only around 13 circumbinary planets have been confirmed to orbit them both. This contrast is what makes circumbinary planets so astonishing. They are not just rare, they are cosmic survivors in one of the harshest gravitational environments imaginable. binary star systems themselves come in an extraordinary variety. Some are close binaries, where the stars orbit each other at distances smaller than the distance between Earth and the Sun. These stars can circle one another in just a few days, tugging violently at their shared gravitational center. Others are wide binaries, separated by hundreds or thousands of astronomical units, taking centuries or millennia to complete a single orbit. Between these extremes lies a dazzling diversity. Binaries of nearly equal mass, pairs where a massive star is joined by a faint red dwarf, and even systems where one star has already died, leaving behind a white dwarf, neutron star, or even a black hole as its partner. With such abundance and diversity, one might expect planets orbiting these systems to be plentiful. But the reality is sobering. Despite the countless opportunities, planets orbiting both stars remain almost invisible. The reason lies in the violent nature of binary environments. For planets to form, a protoplanetary disk of gas and dust must settle around the young stars. In single-star systems, this disk can stabilize and gradually give rise to planets over millions of years. In binary systems, however, the gravitational tugging of two stars disrupts the disk, stirring it violently and making the process of coalescence extraordinarily difficult. The odds are stacked against planets forming in the first place. And even if they do form, survival is far from guaranteed. The competing gravitational pulls of the two stars create regions of instability where orbits cannot last. Only planets that form or migrate into the narrow zones of stability, well beyond the star's gravitational chaos, can endure for billions of years. This filtering process ensures that while binary stars are abundant, circumbinary planets are extraordinarily rare. The numbers tell the story clearly. With half of all stars bound into binaries, there are billions upon billions of double-star systems across the Milky Way. Yet only around 13 confirmed planets orbit both stars. That makes circumbinary planets not just one of the rarest classes of exoplanets, but also one of the most improbable. Each confirmed discovery is like finding a needle in a cosmic haystack, an object that has beaten almost impossible odds to survive. They are not just rare. They are exceptional, carved by gravitational forces that should have destroyed them, but instead sculpted their orbits into resilience. This rarity gives circumbinary planets a special status in astronomy. They are not only scientific curiosities, but also proofs of possibility. Their existence demonstrates that planets can emerge in environments we once thought too chaotic, reshaping theories of planet formation. They also highlight how deceptive appearances can be in the universe. If someone told you that binary stars are everywhere, you might assume circumbinary planets should be equally common. But reality shows us a different picture. Stars may pair off in abundance, but the worlds that orbit them both are fragile exceptions, survivors of environments that reject most attempts at planetary formation. And there is another layer to this story: detection bias. Just because we've confirmed only around 13 doesn't mean there aren't many more. The challenges of detecting them, irregular transits, complex orbital geometries, noisy stellar light curves, mean that our current methods are likely missing the majority of these planets. It is entirely possible that circumbinary planets are more common than we think, but remain hidden from our instruments. If so, then our current count is not just a reflection of rarity, but of the immense challenge of observing them. Even so, their numbers will never rival those of planets around single stars. Their survival requires such delicate balances that nature can only produce them sparingly, making each confirmed world a precious jewel in our cosmic catalog. So, when we speak of circumbinary planets, we are not just describing exotic orbits. We are speaking of cosmic survivors, worlds that endured where destruction seemed inevitable, worlds that found stability where chaos was the rule. Among billions of stars and countless binaries, only around 13 have revealed their secrets so far. Their scarcity is what makes them treasures, each one a testament to the universe's ability to carve order out of turbulence and beauty out of instability. The story of circumbinary planets is not just one of rarity, but of fragility. These worlds, orbiting two suns at once, exist in a state of perpetual tension, caught between competing gravitational masters. Their very survival depends on a fragile balance, a razor-thin line between stability and destruction. One small change, a shift in orbital resonance, a nudge from another body, or even the gradual evolution of their stars, could be enough to tip the scales and fling them into deep space, banishing them from the home that gave them birth. It is this precariousness that makes the around 13 confirmed circumbinary planets so remarkable. Each one is not just rare, it is living proof of survival against overwhelming odds. The physics of this fragility begins with the binary stars themselves. In a single star system like ours, the Sun acts as a steady anchor, holding planets in predictable elliptical orbits, but in a binary system, there is no single anchor. Instead, two stars orbit one another around a shared center of mass, their combined gravity shifting constantly in subtle ways. A circumbinary planet must orbit far enough away that it feels the star's gravity as if they were a single source. If it strays too close, however, it enters the chaotic zone, a region where gravitational pulls from the two stars fluctuate wildly, disrupting stability. In this zone, even the tiniest change can cascade into disaster. A planet might be nudged into an unstable orbit that decays over time, eventually sending it spiraling into one of the stars or ejecting it entirely into interstellar space. This instability isn't just theoretical. Computer simulations of binary systems show that even small perturbations, like the presence of another planet, a passing star, or the slow drift of the stars themselves as they age, can destabilize orbits that once seemed secure. A planet that has circled its twin suns for millions of years can, in principle, be ejected in a matter of thousands of years if the balance tips. The fact that any circumbinary planet survives long enough for us to discover it is therefore extraordinary. They are survivors in the truest sense, balancing on the knife's edge of gravity for billions of years without falling. Another dimension of fragility comes from the stars themselves. Stars are not static. They flare, expand, contract, and evolve over time. A binary pair might begin with two relatively calm stars, but as they age, one could swell into a red giant, altering the gravitational balance of the system. This change could shift the habitable zone, destabilize planetary orbits, or even engulf nearby worlds. The planets we see today may not survive the future evolution of their suns. The around 13 circumbinary planets confirmed so far are thus snapshots in cosmic time, stable now, but with uncertain futures shaped by forces far beyond their control. What makes this fragility even more fascinating is that circumbinary planets can exist in long-term resonance patterns that keep them stable until something disrupts the rhythm. Much like Jupiter's gravity keeps certain asteroids locked in resonance in our solar system, binary stars can shepherd circumbinary planets into orbits that repeat harmoniously with the star's motion. But resonance is delicate. A tiny shift, perhaps caused by gravitational interactions with another body in the system, can throw the planet out of its safe rhythm and into instability. It is a balance as delicate as a tightrope walker in a storm, steady only so long as no gust of cosmic wind blows too hard. From a broader perspective, this fragility underscores the rarity of discovery. For us to find around 13 circumbinary planets, each one had to not only form in the hostile environment of a binary system, but also survive billions of years without being ejected. Most attempts at circumbinary planet formation likely failed long ago, their fragments scattered into interstellar space or consumed by their stars. The survivors we see today are the exceptions, the lucky few that managed to thread the needle of stability. They are the winners of a cosmic lottery where the odds are stacked overwhelmingly against success. Philosophically, there is something deeply humbling about this precariousness. On Earth, we take stability for granted. Our sun rises and sets with clockwork precision. Our orbit remains steady year after year, and life flourishes under the illusion of permanence. But circumbinary planets reveal a harsher truth. Stability is not guaranteed. It is fragile, conditional, and easily undone. These worlds exist in constant peril, and yet they endure, a testament to resilience in the face of chaos. Their fragility also raises haunting questions about what might lie beyond the ones we know. How many circumbinary planets have been lost to instability, ejected into the dark between stars as lonely wanderers? Could the galaxy be filled with such orphans, planets that once basked in the light of two suns but now drift eternally in the cold void? If so, then the around 13 we've confirmed are not only survivors, but also reminders of countless others that perished unseen. The fragile balance of circumbinary planets is what makes them so extraordinary. They are not just planets, They are tightrope walkers of the cosmos, balancing delicately between two gravitational giants. One small misstep could destroy them, but instead, they persist. Their very existence is proof that even in the harshest environments, order and survival are possible, if only just barely. The fragile balance of circumbinary planets makes them feel like impossible survivors, but their importance goes far beyond rarity or beauty. They matter because they challenge and expand our very theories of planet formation. For decades, scientists built models of how worlds come into being, based largely on our own solar system. A single star surrounded by a protoplanetary disk of gas and dust gradually coalescing into planets under the steady tug of one gravitational anchor. This model worked well for explaining most of the thousands of exoplanets discovered so far. But circumbinary planets stand as living contradictions to these expectations. If planets can form in the violent chaos of two stars tugging at each other, then they can form almost anywhere. These worlds force us to rewrite the rules of cosmic creation. To appreciate why circumbinary planets are so important, we need to look at how planets typically form. In a young star system, the leftover dust and gas from the star's birth settles into a rotating disk. Within this disk, particles collide and stick together, forming pebbles, then planetesimals, and eventually full-fledged planets. Around a single star, this process is relatively stable, but in a binary system, the picture becomes far more turbulent. The two stars orbiting one another stir the disk violently, sending shockwaves through the material and disrupting the calm needed for coalescence. Early models suggested that instead of forming planets, these disks would remain unstable, with collisions shattering planetesimals before they could grow. The result, theorists predicted, was that circumbinary planets should be vanishingly rare or perhaps non-existent. And yet, here we are, with around 13 confirmed examples that prove otherwise. These discoveries matter because they demonstrate that our universe is more inventive and adaptable than our theories once allowed. Planet formation, it seems, is not a fragile process that only works under perfect conditions. It is a robust, resilient mechanism that can operate even in hostile environments. If nature can assemble stable planets in the gravitational chaos of a binary system, then perhaps it can assemble them in triple star systems, near pulsars, or in other unlikely settings we have yet to explore. Circumbinary planets, in this sense, expand the canvas of possibility. The fact that these planets exist also reshapes our understanding of protoplanetary disks. Observations with powerful telescopes have shown that disks around binary stars often contain gaps or cleared-out regions, carved by the star's gravitational interactions. For years, astronomers assumed these gaps would make planet formation impossible. But circumbinary planets suggest otherwise. They may form farther out in the disk and then migrate inward until they settle in stable orbits beyond the critical radius. This migration theory explains why many of the confirmed circumbinary planets orbit just outside the zone of instability. They were born in safer regions and then shifted inward until gravitational balance locked them in place. In other words, these planets are not accidents. They are products of cosmic engineering, shaped by forces that both threatened and protected their survival. The implications go even deeper when we consider the sheer abundance of binary stars. With half of all stars in the galaxy belonging to multi-star systems, the discovery of circumbinary planets means that vast new frontiers of planetary systems may exist. If we had clung to the old theories that ruled out such planets, we might have overlooked billions of potential worlds. Instead, circumbinary planets remind us that our galaxy is richer and more diverse than we once thought. Each discovery broadens the scope of where we might search for planets, and by extension, where we might one day search for life. Another reason they matter is that they test the limits of stability in orbital mechanics. By studying these planets, scientists refine their models of how gravity operates in complex systems. The fact that circumbinary planets can maintain long-term stability tells us something profound about the interplay of forces in binary systems. These insights don't just help us understand exoplanets, they also improve our grasp of astrophysics as a whole, from star formation to the dynamics of galaxies. In many ways, circumbinary planets are natural laboratories where the universe demonstrates the extremes of physics in action. Philosophically, circumbinary planets also matter because they shatter our tendency to assume Earth's circumstances are universal. For centuries, humanity imagined the cosmos as a place of orderly solar systems, much like our own. Then we discovered hot Jupiters, gas giants orbiting perilously close to their stars, and realized planetary diversity was far greater than expected. Circumbinary planets push that realization even further. They tell us that nature does not conform to our categories. Worlds can exist in conditions we once considered impossible. If planets can orbit two stars, then perhaps the boundaries of possibility are far broader than we can yet imagine. These planets matter because they reignite our imagination. Science fiction has long envisioned twin sun worlds, from the iconic sunsets of Tatooine to countless other depictions of alien skies. When Kepler confirmed the first circumbinary planet, it was as if fiction had stepped into reality. Suddenly, the fantastical became factual, and the universe felt stranger, richer, and more wondrous. In a way, circumbinary planets matter not just for the data they provide, but for the sense of wonder they restore. They remind us that the universe is still capable of surprises, that the unknown still hides treasures waiting to be found. The importance of circumbinary planets lies not only in their rarity, but in their defiance of expectation. They matter because they prove that planet formation is not confined to calm, orderly environments. They matter because they expand the boundaries of where planets can exist, and they matter because they hint at something profound. If planets can form here, in the gravitational crossfire of two stars, then perhaps planets, and even life, can form almost anywhere. The significance of circumbinary planets does not stop at testing theories of planet formation. Their importance extends deeper into the very fabric of stellar astrophysics itself. These rare worlds are not only laboratories for understanding how planets can arise in chaotic conditions, they are also keys to unlocking the mysteries of binary stars. Studying circumbinary planets allows scientists to see binary systems in new ways, revealing how stars interact, how they evolve together, and how their gravitational partnership shapes the cosmos. In essence, circumbinary planets are not just about planets. They are windows into the lives of the stars they orbit. Binary stars are fascinating in their own right. Unlike our Sun, which lives in solitude, most stars in the galaxy belong to pairs or larger families. These stellar duos are born together, often from the same collapsing cloud of gas, and they remain bound for billions of years in an intimate gravitational dance. Sometimes the stars are nearly equal in mass, moving gracefully around their shared center of mass like two dancers spinning in perfect synchrony. Other times, one star is much larger, dominating the system, while its smaller partner traces a tighter orbit. The dynamics between them can range from serene to violent. Close binaries can exchange material, flare up in bursts of energy, or eventually collide, while wide binaries orbit at vast distances, barely tethered by gravity. But to fully understand how these systems evolve, astronomers need more than just theoretical models. They need observational anchors. This is where circumbinary planets come in. When a planet orbits a binary system, it acts like a cosmic tracer, providing astronomers with incredibly precise information about the stars it circles. Every transit of the planet across the stars reveals subtle details about the system, the timing of eclipses, the gravitational wobbles, and even the slight changes in orbital shape over time. These details allow scientists to refine their understanding of how binary stars move and interact with one another. For instance, by monitoring circumbinary planets, astronomers can measure the exact orbital periods of the stars with astonishing precision, sometimes down to fractions of a second. This, in turn, helps reveal whether the stars are exchanging mass, losing angular momentum, or gradually spiraling closer together. Without the planets as tracers, such measurements would be far harder to achieve. One of the most profound lessons circumbinary planets teach us is about star system evolution. Binary stars are not static, they evolve, sometimes dramatically. As stars burn their fuel, they expand, contract, and change in brightness. In a binary system, these changes affect not only the individual star, but also its partner. A star that swells into a red giant may begin transferring material to its companion, altering both stars' evolution. This process, known as mass transfer, can eventually lead to novae or even supernovae. By observing circumbinary planets in such systems, astronomers gain a unique vantage point to witness these transformations. If a planet's orbit shifts slightly, It can signal that the star's mass distribution has changed, providing evidence of ongoing stellar evolution. Another important insight comes from the stability of circumbinary planets' orbits. Their survival over billions of years demonstrates that binary stars, despite their apparent chaos, can achieve long-term stability in their orbits. This has major implications for our understanding of how stars form and evolve together. The fact that planets can remain bound to binary pairs suggests that the stars themselves are not as disruptive as once thought. Instead, they evolve in predictable ways that allow planetary orbits to adapt and persist. In other words, the presence of circumbinary planets confirms that binary stars, while complex, are not destructive by default. They can sustain ordered systems just as well as single stars. Circumbinary planets also shed light on the distribution of mass in binary systems. When two stars orbit each other, their gravitational influence depends on their relative masses. By studying how a planet moves around both stars, astronomers can calculate these masses with great accuracy. This is crucial because stellar mass is the single most important factor in determining a star's lifetime, luminosity, and ultimate fate. With circumbinary planets as measuring sticks, scientists can refine stellar models and better predict how different types of binary systems will evolve over cosmic time. There's also the question of angular momentum, the energy of rotation and orbit that binary stars share. Over time, binary systems can lose angular momentum through interactions with surrounding material, magnetic braking, or gravitational radiation. These losses can cause the stars to spiral closer together, eventually merging in spectacular events. Circumbinary planets act as witnesses to this slow process. By monitoring their orbits, astronomers can detect tiny drifts in the star's motion that reveal how angular momentum is being exchanged or lost. In some cases, this information may even foreshadow dramatic stellar mergers billions of years in the future. From a broader cosmic perspective, circumbinary planets also help us understand how stellar multiplicity shapes galaxies. Since nearly half the stars in the Milky Way belong to binaries, learning how these systems evolve is essential to understanding galactic evolution as a whole. Do binary stars disrupt planetary formation, reducing the number of habitable worlds? Or do they provide additional pathways for planets to arise, perhaps even fostering unique types of planetary systems we cannot imagine? Circumbinary planets provide real data to answer these questions. Each one discovered adds a piece to the puzzle of how stars and planets coexist in a universe where binaries are the norm rather than the exception. The educational value extends beyond astrophysics into the philosophy of science itself. For decades, astronomers debated whether circumbinary planets could exist at all. The theoretical arguments against them seemed overwhelming. Yet the around 13 confirmed examples prove that nature often defies human expectation. In studying them, we not only learn about stars, we learn humility. We are reminded that the cosmos is not bound by our preconceptions. Stars and planets do not follow the neat patterns we imagine for them. Instead, they reveal patterns far stranger, richer, and more complex. And then there is the cultural impact. By confirming the existence of planets orbiting two stars, astronomers gave the world a tangible link between fiction and reality. The twin sunsets of Tatooine, once only a vision of imagination, became grounded in fact. But beyond the romance of double sunsets lies something deeper. These planets offer us insight into how the most common type of stars in the universe actually live their lives. They are not just curiosities, they are tools, teaching aids written into the sky, helping us decode the dynamics of binaries. In short, circumbinary planets matter not only because they are rare and beautiful, but because they teach us about stars themselves. They reveal how binary stars interact, how they evolve, and how they can sustain stability even amid apparent chaos. They sharpen our models, refine our measurements, and expand our sense of what kinds of systems are possible. Each circumbinary planet discovered is like a cosmic classroom, where the lessons are written not in chalk or ink, but in the faint dimming of starlight billions of years old. So, when we gaze upon the data of these planets, we are not only seeing rare worlds, we are seeing into the very hearts of stars, watching their dance unfold across time, and learning how the most common stellar partnerships in the galaxy shape the universe around them. Circumbinary planets are thus more than survivors. They are storytellers, narrating the hidden lives of stars in a language we are only just beginning to understand. The scientific lessons circumbinary planets teach us about stars are invaluable, but inevitably, the human imagination drifts toward the question that lingers behind nearly every discussion of distant worlds. Could they host life? It is a question that blends science, speculation, and wonder, for these planets orbit in environments so alien to our own that imagining life there feels like peering into another universe. And yet, if life has taught us anything, both on Earth and in the cosmos we study, it is that it can be astonishingly adaptable. The prospect of alien organisms evolving beneath the glow of two suns may sound like fantasy, but it is not beyond the realm of possibility. To begin with, the conditions for life on circumbinary planets are undeniably challenging. Two suns mean not only shifting amounts of radiation and heat, but also unpredictable cycles of light and darkness. A planet might experience double sunrises, staggered sunsets, or stretches of twilight when one star lingers above the horizon while the other dips below. For Earth organisms, whose biological clocks are synchronized to the reliable cycle of a single sun, such irregularity would be disorienting, if not outright hostile. Yet, alien organisms would not be bound by our biology. They would evolve in direct response to their skies, building resilience not to stability, but to change. Consider the concept of double shadows. On a circumbinary world, every object on the surface would often cast two overlapping shadows, each pointing in a different direction depending on the positions of the suns. Sometimes the shadows would blur into one, sometimes they would stretch apart in eerie symmetry. For alien life, this would be the norm. Predators and prey might evolve eyesight tuned to track not one, but two shifting shadows. Camouflage strategies could be vastly more complex, with organisms adapting color patterns that distort under dual lighting, tricking observers into losing track of their form. Life under two suns would not only adapt to light, it would adapt to the geometry of light itself. Then there is the matter of day cycles. On Earth, the day-night rhythm governs almost every living process, from the opening of flowers to the sleeping cycles of animals. On a circumbinary planet, day cycles could be wildly unpredictable. There may be stretches of near-constant light, interrupted by sudden plunges into darkness when both stars set close together. Or nights might never be truly dark, illuminated by one lingering sun even as the other disappears. Life here would not evolve around the expectation of consistent days and nights, but around the ability to survive and thrive in flux. Biological clocks might be flexible, allowing organisms to rapidly switch between active and dormant states. Some creatures could evolve to store energy during periods of double daylight, then enter hibernation-like phases during extended nights. Others might flourish in twilight conditions, making use of the dim, blended light that Earth life would find alien and faint. The climate extremes of circumbinary planets would also shape evolution in radical ways. With two sources of heat, temperatures could swing violently. During periods when both suns blaze overhead, surfaces might reach scorching highs. When one or both stars set, or when they eclipse each other, temperatures could plummet rapidly. Life would need extraordinary adaptability to withstand these shifts. Perhaps thick, reflective exoskeletons or scales could protect organisms from searing heat, while insulating layers could preserve warmth during sudden chills. Burrowing life forms might retreat underground during the harshest conditions, emerging only during stable intervals. Plants or plant-like organisms might evolve the ability to photosynthesize across a broad range of wavelengths, drawing energy efficiently from both stars, even if one radiates redder light and the other bluer. Alien ecosystems could also operate under multiple seasons, layered upon each other. Instead of the steady tilt-driven seasons of Earth, circumbinary planets would experience cycles tied to the relative positions of their stars. A year could include periods of intense double-star summers, when both suns align to flood the surface with heat, followed by cooler single-star winters, when only one dominates. Life might evolve migration patterns not based on latitude, but on the geometry of starlight. Entire ecosystems could move across the planet's surface, following zones of moderate climate as they shift with the star's motions. In such worlds, adaptability would not be an advantage. It would be a requirement for survival. The question of intelligent life on circumbinary planets opens even more fascinating doors. How would a species under two suns develop concepts of time? On Earth, calendars and clocks emerged from the regularity of one sun and one moon. On a circumbinary planet, time would be fractured into overlapping cycles: the orbit of the planet around its stars, the stars' orbits around each other, the rise and set of two suns on different schedules. Alien civilizations here might build entire systems of thought, philosophy, and science around the complexity of their skies. Their art and architecture might embrace symmetry and doubling, shaped by the ever-present reminder of two suns above. Speculatively, such civilizations might also evolve in ways more resilient than ours. Living under constant change would make adaptability second nature. Where humans often struggle with unpredictability, alien beings forged under dual suns might embrace it as the foundation of existence. Their biology, culture, and worldview would all be conditioned by an environment that never settles into a single rhythm. In that sense, life under two suns might not only be possible but could produce beings with a perspective profoundly different from ours, creatures who see chaos not as threat, but as harmony. Of course, the greatest obstacle is the habitable zone problem. For life as we know it, liquid water is essential, and on circumbinary planets, habitable zones shift constantly. Yet, if even a narrow band of stability exists, and if a planet or moon can maintain thick atmospheres or oceans to buffer against extremes, then life might carve out a niche. The around 13 circumbinary planets we know today are mostly gas giants, unlikely to host life themselves. But their moons, if large and stable enough, could potentially be cradles of biology. If so, then alien life beneath two suns might not be found on the planets themselves, but on the satellites that orbit them, basking in the strange dual rhythms of light and dark. Ultimately, when we speculate about life under two suns, we are reminded of how narrow our imagination often is. On Earth, life has flourished in boiling vents, acidic lakes, frozen tundras, and even radioactive waste, places once deemed uninhabitable. If life is this resilient here, why not on circumbinary planets? The dual shadows, the shifting cycles, the chaotic climates might seem insurmountable to us, but to life born there, they would be the natural order. Creatures with bodies built for light that bends and overlaps, plants that thrive on inconsistent cycles, civilizations that rise and endure under ever-changing skies. These are not impossibilities, but logical outcomes of evolution shaped by twin suns. After speculating about the possibility of life beneath two suns, we arrive at a sobering reality that cements just how extraordinary circumbinary planets truly are. Despite decades of searching, despite the immense power of telescopes like Kepler, and despite the fact that nearly half the stars in our galaxy belong to binary systems, astronomers have confirmed only around 13 circumbinary planets in the entire universe we've explored so far. This makes them not just rare, but the rarest of the rare. Cosmic survivors, perched delicately in environments where nature seems almost determined to erase them. Their scarcity elevates them from mere astronomical curiosities to treasures of the cosmos, jewels so elusive that each discovery feels like a miracle against overwhelming odds. To put their rarity in perspective, consider this. Scientists have identified more than 5,500 confirmed exoplanets to date, with thousands more candidates waiting for confirmation. These planets range from scorching hot Jupiters hugging their stars, to rocky Earth-sized worlds orbiting at just the right distances, to ice giants drifting in outer reaches. Yet, among this vast catalog, the number of circumbinary planets barely breaks into double digits. That's less than 1% of all confirmed exoplanets, and in truth, far less when you consider the billions of stars scattered across the Milky Way. If exoplanets as a whole are common grains of sand on the cosmic shore, then circumbinary planets are like rare seashells polished smooth by chance, a handful scattered across an endless beach. Why does this rarity matter? Because it tells us something profound about the universe's ability to create stability in the most chaotic environments. Binary stars are everywhere. They make up a huge fraction of the galaxy's population. If planets orbited them with the same frequency they orbit single stars, we should have discovered hundreds by now. The fact that we've confirmed only around 13 tells us that the conditions required are incredibly restrictive. Everything must align perfectly. The protoplanetary disk must survive long enough to form planets. The planet must find a stable orbital niche beyond the gravitational chaos zone, and the orbit must remain intact for billions of years. And even if all of that happens, we still must be fortunate enough for the planet's orbit to align with our telescopes here on Earth. The fact that even one has been found is remarkable. The fact that more than a dozen exist is staggering. This scarcity also makes circumbinary planets a symbol of survival. They are not simply rare because they are difficult to detect. They are rare because so many potential circumbinary planets likely never made it past infancy. Most would have been torn apart during formation, flung into interstellar space, or consumed by one of their suns long before we could hope to see them. The around 13 that remain are the survivors of countless failed attempts, the final proof that even in environments stacked against them, persistence is possible. They embody resilience at a cosmic scale. Their rarity also reframes the way we think about the galaxy. In a universe filled with billions of star systems, we often imagine planets to be plentiful. And indeed, they are. But circumbinary planets remind us that not all worlds are equally likely. Some categories of planets are abundant, forming easily and surviving in large numbers. Others, like these, are born only under the strictest of conditions. This stratification of rarity gives us a richer, more nuanced picture of the cosmos. It is not just teeming with planets, but with hierarchies of possibility, where certain types of worlds emerge frequently, while others are vanishingly scarce. The title, Rarest of the Rare, also carries a cultural weight. For centuries, humans dreamed of twin-sun worlds in myths and stories. Science fiction turned them into iconic symbols of the alien and the exotic. And then, when science finally confirmed their existence, we found that they are not common at all. They are jewels hidden deep in the fabric of the galaxy, revealed only by the most precise and patient observation. The double sunset is not just a poetic image, it is a vision granted to only a handful of planets out of billions. To glimpse such a sky would be to witness one of the rarest experiences the universe can offer. What does it mean then, that only around 13 are confirmed? It means that every circumbinary planet we find is more than just a number in a catalog. Each one is a singular discovery, a case study in defying the odds. Kepler 16b, Kepler 34b, Kepler 35b, Kepler 38b, and the others in this tiny group are not just planets, they are trailblazers. They prove the impossible is possible. They expand our definitions of what planetary systems can be. And they remind us that even after centuries of astronomy, the universe still has surprises tucked away, waiting for the right eyes to find them. Ultimately, circumbinary planets earn their title as the rarest of the rare because they embody everything that makes astronomy both humbling and exhilarating. They are scarce, fragile, and hard to detect, yet their existence rewrites textbooks and stirs imaginations. They show us that the universe is not obligated to be simple or abundant in all things. Sometimes, it saves its most spectacular wonders for only a chosen few, scattered so sparsely that finding them feels like uncovering secrets hidden for billions of years. And that is what makes them precious. Not just their rarity, but the reminder that the cosmos is a place where the improbable thrives. Throughout this journey, we have traced the story of circumbinary planets from their improbable birth in turbulent disks of dust and gas, to their fragile survival against the relentless pull of dual suns, to their role in reshaping everything we thought we knew about planets and stars. They have revealed to us skies of double sunsets, climates of extremes, and orbits that walk the knife's edge between stability and chaos. They have shown us that even in the most hostile and unstable environments, the universe finds ways to create order, balance, and beauty. And perhaps most importantly, they have reminded us that the cosmos is not uniform, not predictable. It is filled with wonders so rare they can be counted on the fingers of two hands. Among the thousands of exoplanets discovered so far, circumbinary planets stand apart as the rarest of the rare. Despite the abundance of binary stars across the Milky Way, we have confirmed only around 13 of these worlds, around 13 survivors in a galaxy of billions. Each one is a treasure, not just because of what it is, but because of what it represents: possibility against improbability, stability against chaos, resilience against destruction. These planets are cosmic proof that nature is more inventive than our imagination, capable of sculpting stable orbits where instability should reign, capable of writing stories of survival in the harshest of environments. And yet, their rarity also humbles us. For every circumbinary planet we confirm, there may be countless others we will never see, hidden by geometry, lost to instability, or wandering the dark void after being flung from their homes. The handful we know are not the whole story, but the survivors we have been lucky enough to glimpse. They stand as symbols not just of science, but of chance, of discovery, and of the universe's tendency to keep its greatest wonders just out of reach, forcing us to look deeper, longer, and harder. Circumbinary planets also invite us to reflect on ourselves. We live on a world blessed by stability. One star, one rhythm of day and night, one habitable zone that has nurtured life for billions of years. Compared to the precarious orbits and shifting climates of circumbinary worlds, Earth feels like an oasis of calm. Their rarity makes us appreciate our own uniqueness, while their survival reminds us that fragility is not the same as impossibility. If life can flourish in extremes here, perhaps life, strange, resilient, unimaginable, might one day be found even in the light of two suns. In the end, circumbinary planets are more than astronomical curiosities. They are stories written in starlight, narratives of survival and rarity that challenge our theories, expand our imagination, and deepen our awe. They stand as reminders that the universe is not built for our convenience. It is built in complexity, in improbability, in miracles of balance that defy expectation. Each double-sun world is a whisper from the cosmos, telling us that reality is stranger than fiction, that beauty thrives in the rarest places, and that the most astonishing truths are often hidden where we least expect them. And so we close with the perspective they give us. Among billions of stars and countless worlds, just around 13 circle two suns. They remind us how fragile, rare, and astonishing the universe truly is. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.